morning, everyone. Thanks, Tim, for that nice introduction. When they gave me the director title, I didn't have to go through the forced lobotomy, so I can no longer claim to be able to code, at least professionally, maybe on the side for fun. And as Tim said, I've been doing this embedded Linux stuff for a long time, and I was commiserating with some others about how it used to be in the good old days of working on processors and talking about how it's like today. And in that commiseration, one of the guys that works for me is working on the display driver for OMAP, and I worked on a frame buffer driver for a PowerPC chip a long time ago. And I was telling him about what it took to get a frame buffer driver going, and he kind of looks at me funny and goes, "Wait, that's so simple. What are you talking about?" And he explained what he's doing. I'm going, "Oh my goodness, how do you even get that done with one guy and the amount of time that he has?" And so that's what started me thinking about this topic of complexity, and talking to a few people about the same kinds of things. How can we get Linux developed for these SoCs today in a timely fashion so that OEMs, the device manufacturers, can actually get their device out? And when Tim started talking about a keynote speech, he had a similar topic in mind, so it turned out to be good. So with that in mind, I want to take a look at the block diagram. So of the PowerPC chip that I mentioned, it was the PowerQuick 1, circa 1995. And if anybody can figure out when the Linux patch was submitted upstream for that, I will buy them a beer, but the first one only. And it was quite a while ago. So if you compare that to the latest OMAP chip, OMAP 5, you've got a single core PowerPC with a few devices. Back then I thought it was quite a lot, but compared to the block diagram on the right there, it's completely different. And it's not too important to read the text. I know it's very small. We'll look at a bigger block diagram in a minute here. But the important thing is to see the difference in the number of blocks and how it came to be here. So what we're talking about in today's SoCs, using OMAP as examples in SLAM from TI, but this is a fairly typical set of things that are on the SoC. So we've got dual core A15s, there's a GPU, there's offload processors, so we've got other Cortex ARM parts in there, as well as a DSP. And then very specialized IP blocks for video processing, camera imaging processing, that type of stuff, as well as a normal set of I/O blocks. So what makes these SoCs complex? And if you see the difference, so we go mid-90s from when that chip was released, the PowerQuick 1, to today. That's a big time difference, but there's a lot more stuff that we're squeezing into this chip. We have to fit more things in a smaller space, and we have to fit a lot more processing power in. And the driving factors behind this design of the hardware is you're squeezing more in, but you have this physical limitation on size, about how much you can actually fit in there, which drives the process nodes down smaller and smaller. As we get the process nodes smaller, you have more limitations and more things to deal with: power, thermal. And another big change from that time, the PowerQuick 1 days to today, is a lot more IP blocks are being developed by third parties, and you're licensing those. So you're taking all these things, you're squeezing it in, and the SoC manufacturers are focusing more on differentiation in specific areas. So it's more focused differentiation on specific areas of technology that are really important in that area. So we go back and we look at what's important to TI. You can kind of see that we're big in multimedia and audio, and so all of our IP blocks are focused in that area. And it's offloaded from the ARM processor. So as a result, there's a lot of specialized software that needs to go with that specialized hardware. And that really drives another level of complexity from the software point of view. And how do we make that specialized software available to generic frameworks, generic applications, so people can take advantage of it and actually use it? And then compute requirements have dramatically increased. So we just saw on the block diagram there, we have 2 A15s, all the other ARM M4s, the GPU, and it just gets more and more. If you look at the Apple chip, the latest Apple chip, the A6, they have a 3-core GPU plus the 2 ARM cores, and they're talking about the quad core coming out soon. Many of the other SoC vendors have quad core ARM cores up today. So what are these complexity variables that are driving the problem here? When you have more hardware, it requires more software, which requires more time. But the time to market pressure is not shrinking. When we work with OEMs, they don't tell us, oh yeah, because you have all this stuff and we want your software to work and we want the hardware to work, go ahead and take more time and we'll get the market and we get the market. No, it's shrinking, it's going the other way. So we have this problem of we're doing more, but we have less time, but it's taking more time. And how do you solve those variables? It's an equation that is not easily solved. Another aspect is that it's not getting cheaper to do this. It's costing more. As we shrink the process nodes, the semiconductor fabs, and anybody that's developing their own process has to incur that cost. That's a pretty big cost to incur, and it's not something that just one company can do, which is why we moved to fabless semiconductors. So what does this go translate to the actual software problem? So the hardware is there's more in it, there's more complexity in the pieces and how they fit together. It takes more time, more people to get that done. But the hardware guys don't care. And this is part of the requirements, that you have to have this to compete in the market, for the OEMs to buy your part and to then deliver that as a complete solution to the market, which is being bought by consumers or whatever market you're delivering into. So it becomes the software problem. It is our problem to solve, to make this complex SoC usable, not only by the kernel and the software developers, but by application developers and whoever else needs access to these features. Then we can go into an OEM product and we ship to market, and it's the cycle that employs us all. So as we look at all these things, and going back to the block diagram, there's a lot of things here. We always ask ourselves, how do we get all this software done in the time frame that we have to deliver to our customers? And the answer is it cannot always be developed, and we have to break it into phases, as with any software project. An important part of the breaking down into phases is which pieces does it make sense to send upstream. It's a very difficult problem to balance that product time frame with your desire to get as much of the kernel upstream as possible, as much as your hardware support upstream. And so you have to take into account several things in doing this. What pieces are generic and can be leveraged by a number of people? Is it something that's just specific to TI, or is it something that's specific to every ARM SoC? Or is it generic to how anybody that's doing an audio offload engine would need to use that hardware and expose that software? So you take a look through these questions, you have to ask yourself, how do some of the features become product only? Say, okay, it doesn't make sense to upstream this today. Let's go ahead and leave that in our software product. This piece, let's go ahead and upstream. And then how does the kernel evolve to handle this complexity? So it's not something that necessarily is going to just work out of the box today. You may have to evolve certain subsystems of the kernel to be able to handle the complexity of your hardware, which is not going to happen overnight. So that's yet another time frame that you have to take into account. Evolving the frameworks, the subsystems within the kernel, versus your OEM, your customer requirements, versus your just plain old, let's get this board and just support it upstream. And then, so assuming we can figure that out, can we evolve it fast enough? All hardware has a limited time frame. Even though there's lots of SoCs supported upstream today, not all of them are used in new design wins, and some become irrelevant to SoC manufacturers and the OEMs, even though it may be relevant to the community. And so if we can't evolve the kernel fast enough, or in some of these subsystems fast enough, the hardware then becomes obsolete in the sense of what's important to the semiconductor manufacturer. we're all operating within that time window of when new design wins are important to the semiconductor manufacturer. And that's really the sweet spot of when the software people at companies like TI and others can really invest in doing the software correctly and pushing it upstream. If we can't fit within this window, then we've missed an opportunity, and we have to then ask ourselves again, does it make sense to continue, or should we just move on to the next part? Finally, who is doing all this work? There's a tremendous amount of work that needs to be done to support the ARM cores, how we put the ARM cores together in the SoC, all those different IP blocks that belong specifically to TI, but yet are generic in the same way. We're doing an audio offload engine. A lot of people are doing audio offload engines, and it can be done in a very similar way. So the answer to these questions are not easy, and we need to figure out what we can do to solve some of this stuff. If you look at who is doing all this work, I think it's an interesting trend, and I don't have the numbers for this presentation, but I think it would be interesting to look at. John's presentation, his keynote speech talked about who's the contributors to the Linux kernel. It ranks by company, by developer. He's also broken it down into architecture and what's going on in each of the architectures. And you can see that the semiconductor people are just skyrocketing up. TI went from less than number 10 to above number 10 in the last just 2 years. I think we're at 5 or something now, maybe even higher, specifically with ARM. And that really explains who's doing the work, whose responsibility it is to make all this stuff happen. So what is the solution? So going back to the problem statement of time. We don't have enough time to wait for the hardware to come out, to then start looking at how the kernel is going to be ported to that hardware, to then say we're going to evolve some of these subsystems and take it to solve some of the complexity issues, to address the offload engines or what needs to be enhanced with the ARM cores. And so the only thing we can do here is that the software needs to start earlier, and we can no longer wait until the hardware guys have defined the hardware, let it get to a point of development that's solid and done, to then start figuring out how to port the software. It needs to start at the same time. We really need to completely change how we think and work to make this happen, to really get the kernel ported to the hardware and all these things figured out so that we can get the software upstream and within that window that I mentioned of when it's important to the semiconductor manufacturer. And this is a big change. It's not something that can happen overnight. It's also not something that will happen by any specific means. It's really a social engineering change within the companies. Those of you that are working at the semiconductor manufacturers have to promote and work hard to get that idea that hardware and software should be developed together. That it sometimes even needs to be a software-led relationship for how you're going to develop a framework and then say, here's how the hardware can best work with the software framework. And it's really a relationship between those teams that needs to evolve. At TI, we've been able to, in the OMAP group, have some success here. I think it's really something I hadn't seen before at other companies, at other semiconductor companies, but it's something that it can happen, and it needs to happen, because that's the only way we're going to be able to deliver the software for this complex hardware in a reasonable time frame. So another idea here is that not one company can solve this problem. Not one company can get all of those pieces in that block diagram developed by themselves. Not TI as one company could not go and develop something like RT message and figure out how to best talk to different processors in the SoC and the messaging between the two. You're too focused on how your SoC works, how your SoC is connected, and you've been working with your hardware for a very long time, so you know exactly how it operates. To take that level up and look at how other SoC companies are designing their hardware, to know all the little details that go into how those pieces are connected, you can't do, and it doesn't make sense for you to do as a TI or somewhere else. Instead, it needs to be through a shared engineering organization. And there's two pretty successful ones. The Links Foundation, of course, which is hosting several projects where they're trying to get the shared engineering resources together to design and develop. And also Lenaro, which is a newer organization where it's focused on ARM SoC manufacturers coming together and solving this problem. Another interesting aspect to this was when TI was working with Google and the Android team for ICS, we had what we call a shared engineering, maybe an open engineering discussion, where they took a look at how we were doing the messaging between the different processors in the SoC. And they said, look, we see all the other SoCs out there, and this is not going to work right. You need to make it simpler, you need to do this and that, and some very specific feedback, because they work with so many different SoCs. And so what we were able to do is take that knowledge together and get it re-engineered, refactored, what we call a key message, and then work on getting that upstream. So now we have something that was really a very complex piece of software that was developed internally by TI, maintained internally by TI, into a much more efficient, smaller piece of code that's maintainable and has been submitted to the upstream mainline. And as a result, it reduces our total cost of ownership for that piece of software, and it works for a number of different SoCs that can take advantage of it. So this concept of shared engineering, it goes beyond just the open source community. In the standard posting RFCs, it's really more about getting together and understanding detailed product requirements in a way that can be co-developed and have a method for sharing the resulting IP. How do you assign copyrights to that when two different companies have come together and worked on that kind of thing? And so we've got some great organizations that have started, but really we're going to need more of this. This is a model which I think is the future. We're going to see a lot more from Lenaro. We're going to probably see a lot more projects hosted by the Links Foundation, where it's going to allow this kind of collaboration to solve the problem that all these SoCs are getting more and more complex and more stuff in those things, and there's just no way for any one company to be able to figure out what the right frameworks are to work on that. And so the question that came up as part of this is that, so if we miss that window, does it make sense to upstream at all? We're talking about the window when the SoC companies, the semiconductor companies are doing the investment on that processor. We're not going to be able to get everything upstream in that time frame. It's going to take a much longer time. Does it make sense to even think about to continue upstreaming? But the answer is yes, but we would have to do it differently again. Going back to my point about starting the software earlier. We cannot wait until the chip is done and ready to start our upstream process. What you have to do is actually start much earlier, pre-silicon in that development and getting the right pieces and the frameworks developed. So upstream is very, very critical, even if we're talking about shorter time to market and longer development cycles. We must continue to upstream and make that happen. So, a little example, and I chose the word apocalypse because I wanted to show this slide right here. I don't know if the ones from the US may recognize this, but for those that were not watching it, it's a TV show about the zombie apocalypse where everybody dies and zombies come back to life and you're running for your life. And so that's really what I was getting to. So are we, in this complexity of the SoCs, it's taking longer to get the software running. It takes a lot more effort. We're running out of time for getting that software running on the hardware to OEM requirements so that they can make it to market in time and figure out how to get it upstream in there. All those things kind of fall on each other and build up to a point where the whole thing can just completely fail. Have a complete apocalypse about all these variables that are really unsolvable. And it's not something in the future. It's actually, it has happened in a relatively minor but important way. So you guys may be very familiar if you're following in the Linux community what's going on. But with all the different ARM SoCs that were going upstream to Russell and then up to Linux, there was a complaint about the amount of code that changes in between, because we're constantly refactoring, we're constantly finding that, oh, now this new ARM SoC has this feature, but they did it a little bit different, so we have to duplicate the code and maintain it separately. And what happened was that there was a big complaint that said, you guys need to go and just completely clean up your tree, the ARM SoC tree. Go get it all, so you're sharing code and you're not duplicating effort back and forth. And so there were some good results that came out of it. It's exactly what needs to happen. We had device tree, DMA engine, pin control framework, common clock control framework, and RFQ message, what I mentioned before too. These are all examples of success in being able to take a look at a very complex piece of hardware, find the common areas among them, and then be able to refactor the code, get it developed, and be able to share it. Lenaro had a big part in helping these efforts. Many of the SoC manufacturers and their software engineers contributed, as well as the community in general. So apocalypse isn't always bad. Sometimes it's good to have a little scare to be able to go and react and do something about it. And so again, this is a good example of how we can continue to look at critical pieces of code that make it easier to add SoCs. And it's easier to add new SoCs into Upstream. It becomes easier for the silicon companies to then actually submit Upstream and propagate that cycle of goodness of shared engineering, upstreaming, and open source. So what's next? So there's many things that can come next. One of the things, of course, is that we must reduce this complexity, meaning we cannot have it so that it takes a long time for OEMs to get their products to market. They cannot spin up on your SoC, or TI's SoC, whoever's SoC, learn how to get the software running, figure out how they can do these ports and get their application frameworks talking to the specific ports, to the specific IP blocks. What needs to happen is that us as the software developers need to make it easy for the OEMs, us as the Linux kernel developers and the community in general. It is our job to make it so that people can ship these devices in a timely manner. And what we're going to see that done through is, of course, the community. And again, I think we're going to see more activity out of this shared engineering concept, where it's corporations are coming together in a way to be able to jointly design what happens. And there's an example of this. I was talking to one silicon company a while back, and I was at a software company at the time, and we were trying to figure out how we could have a business relationship partnership. And he said, look, it's just too hard for you to learn how to use my chip, and for me to explain to you so you can develop the software for it. and kind of taken aback because it's too hard. Engineering solve anything. It's not a matter of being hard. But what he meant was that it would take too much time. It doesn't make sense for an independent software person to learn the details of these chips. It would take a tremendous amount of effort. Often, you have to be a part of the development from the beginning of the hardware. You even understand how a lot of these things work. There's undocumented ways that the hardware is structured and put together that affects the software, and the only way you have to know that is to be a part of that company and developing it there. And that's why you see a big surge in the software from the semiconductor manufacturers, and those guys now starting to contribute at Upstream. Because they realize that they have to be the ones to make the investment. They have to be the ones to do the development. You need to be able to make it, again, simple and easy for the OEMs to ship their products. And the only way to do that is to reduce your total cost of ownership, get the code upstream, and be able to really focus on the differentiation that matters. So I think, kind of bring it to a close here, the important thing for us, I think, going through these conferences is to think about the new technology that's being talked about, and areas for us to contribute in. It's really to take a look at it from this point of view. Think about what's coming next when we're talking about putting together new software frameworks. Make sure that the silicon guys that are part of that discussion really try and promote within your own companies, with your relationships with your silicon vendors, if you're at a silicon vendor, your relationship with your hardware team, the fact that we need to be working closer together in order to avoid this complexity of Octopus. The only way we can avoid it is to recognize it and start early and work together with the hardware teams and start focusing on getting this code supported and supported on your SoC as early as possible in the development cycle.
Thank you, Matt. There will be a short break between the sessions to adjust the room.